Hey, welcome, welcome, welcome. This is week 6 of Reproducible Research in R, a course being taught partially online and then partially to students at Louisiana State University, mainly in the Department of Biological Sciences, but you guys are scattered throughout for those that are in the course. So we've gone over a bunch of things so far in previous weeks. We've gone over how to write R code. We've gone over some basics of the Unix command line. We have gone over a little bit on make files. And so we know how to write functions and use R code. And now basically we're going to learn a little bit about code style, and then line profiling and unit testing. So code style is something that helps readability, and a lot of languages have really sort of cemented styles that you're supposed to follow. I feel like R doesn't really necessarily have that, but they do have a style guide and sort of two different style guides that sort of are converging into one. And then the last two things, line profiling and unit testing, have to do with memory management, so making sure that your code, now that you know how to sort of write code, it doesn't go out outside of the capabilities of your machine. And then unit testing, just to make sure that your functions and things are returning sane output. So yeah, let's get into it. I won't talk too much about style because I think I am probably just as bad as anybody about not following some of the style guide. So I'm going to go ahead and share my screen. Share. Okay, so there's my lecture notes, and let's start up our studio. That's how we're going to learn through. Get rid of that date stuff. Switch into a different tiling window thingamabobber. All right, so we got our console, we got our terminal, all that, how that was. It just has to do the bash history. All right, so I actually don't even really need R to talk about the first part. So I go into detail in the lecture notes, and you can follow along at the GitHub, where all the lectures are available online. But a lot of people you learn R, and I know I did, I learned R sort of completely agnostic to understanding coding conventions in terms of how to write well-styled code. And that was not ideal, right? Because good style, maintaining good style keeps code portable across different projects. It makes it clearer and more readable oftentimes. For some things it doesn't matter, and for some things it does. There are entire languages that sort of enforce a certain style, right? Think of languages that are really, really sensitive to spacing, or in order to properly end a line and have it run, you need to use a semicolon. So sometimes style and actual functionality go hand in hand. Most of the things that all of the things that I'm talking about in terms of style here do not affect functionality. And so there's that. And so I included a Hadley Wickham quote here. Good coding, that kind of encapsulates, I think, a lot of people's view on style. Good coding style is like using correct punctuation. You can manage without it, and often we do, but it makes things a bit easier to read. And so that's what we're going to go into. And he also notes that there are a lot of different possible variations. And so that's why I actually really won't be prescriptive with my treatment of code style. So there are different, I thought I linked to it. I should link to it. So there's two style guides as of now. I think Hadley goes over one style guide. It's available in the advanced R book potentially. I'm not sure about that. You can double check me on that. but the other one is the Google style guide. And so Google wrote an R code style guide, which is pretty solid and pretty comprehensive. And the two are sort of convergent to the same thing. So that's good. And so we'll start in terms of style with the idea of naming. So you name objects in the workspace, you also name functions. They should have some things are similar in terms of their style, but generally you want to make sure that if you read the name, you'll be able to tell if it's a function or if it's an object. How I do this is this is me personally, I add a verb to a function every time. A lot of times I'll start with get, so like get, like get mean. And then I know that that's a function that's going to calculate a mean. And meanwhile, objects don't have sort of action verbs associated with them. That's a very simple thing that I do. I mentioned a bunch of other things, so I want to make sure that I'm hitting them all, hitting the high points. Spaces are really bad. And so I think that's what I sort of go into here. I'm going to highlight it if you can read it. So I think a lot of us, especially Windows users, tend to include spaces in file names. Patently bad idea. Like, don't do it. It's bad style. In terms of casing, so what sort of case you use, or sort of word separators for naming of either objects or functions. I think the official style guide says to use, it's either periods or underscores. And I think that's just so clunky when you're typing. So I'm not a huge fan, but there's a reason for it, I'm sure. And so my typical go-to is using lower camel case for both functions and objects. Lower camel case is where the first letter is always lowercase, and then every subsequent new word in describing some object or function, the first letter is uppercase. When I'm naming things that are objects and I want to inform something about the type of data structure that it is, I'll most often put df at the end of a data frame. That's like a silly thing that is unique. It's likely not unique to me. I'm sure tons of other people do that. But something that I sort of really like. Yeah, I note that in terms of naming objects, a lot of the things that are in RStudio and the tidyverse are associated with sort of RStudio's style use underscore a lot, which that's fine. It's really far away on the keyboard, requires the shift key. It's a little clunky when you're typing it. I'm not a huge fan. Those are silly things. Those are silly reasons to be against it. And so now already, I hope you're starting to see this sort of subjectivity in code style. And so it's a good thing to sort of distinguish code style from, I guess, code functionality. So writing a functional, efficient, well-documented code is not necessarily the same thing as writing well-styled code. Another thing that I sort of go over briefly is you don't want to write, and I think I've mentioned this as well, is you don't want to overwrite existing functionality with your variable name. So don't name something C, don't name something T, which stands for transpose. So it takes the transpose of a matrix. And one way you can do this is like start typing out your variable name, like, oh, data, that's a good variable name for data. And then in RStudio, it even says like, oh, that's a function in the utils package. That exists, that's a thing. Let's not overwrite that, because that's not a good idea. And then TS, that's time series. Matrix is the formation of a matrix. So there's tons of other ones where we just don't want to overwrite that functionality because we're going to use that maybe in our script at some point. And then my second sort of separated out thing, or concept or good note, is that to not use completely uninformative variable names. And I'm guilty of this. I've definitely used, and var is actually not a good example because var calculates the variance. So I'm gonna actually move that up to here. But calling something df, just df, is like not a great idea because df is really ambiguous. So hopefully you just name it with a little bit more information there. And we're really bad about this, like sort of collectively. I was reading the software carpentry notes in our sort of reproducible research in R the other day, and they call things, they read in data and call it dat. It's like, that's not a good, it's not the best form, but I'm also guilty of that. I've done that in plenty. And you can see all my R code on Figshare. So I release everything openly, and you can feel free to critique it because some of it was released, what, like 6, 7 years ago at this point, and it was probably when my coding conventions weren't as good as they are now, and they probably are still not good. And yeah, and as I mentioned when naming functions, you sort of attach an action verb to them, and it really helps. That's sort of my my personal idea. Okay, so apart from just naming, in terms of naming files, so R files, the scripts, avoid spaces. I mean, like within R, you can't name an object with a space in it anyways. It just doesn't work like that. So you can say like, my vector equals, and that's just gonna fail. But yeah, spacing is something that R is agnostic to. Like, is that true? I think that's true. Spacing doesn't really matter except for style. And so typically you want to put spaces after commas. And so I already violated this when I defined the vector. Typically it would be after every comma you put a space. Oh yeah, you put spaces around conditional operators, conditionals or operators. What I mean by this, so we went over operators like 1 + 1. That would actually look like that. You want leading and trailing spaces on that, as well as conditionals. And so instead of that, so 1 double equals 1 is 1 equal to 1. We'd want to put space 1 equals double equals 1 space 1. Yeah, so with the formation of, so some things in R, like you sort of, yeah, you can't include spaces. So naming of vectors, you can't include spaces. When you're calling a specific package, you can't include spaces. So if I said, I want to look at dplyr, and I want to look at the function select, that will work, and that shows whatever, but that will not work. Oh, it did work. Wait, no, it didn't. Aaron select data. I don't think it worked. Argument data is missing. Oh, it did work. It just output the same error. And then the second one is a separate warning. But still, whether it works or not, bad style. Don't do it. And then some things, like setting up a vector of length 10, it requires that there not be space, I believe. No, actually that works too. That's crazy. I think it's not going to work because I'm so ingrained in like not putting that space there that I put the space there. I'm like, that's going to error out, and it doesn't. But yeah, it's just me being crazy. That's just bad form. If I saw that in somebody's code, I'd be like, ooh, that is ugly. Yeah, I guess you can put as many spaces as you want. Please don't put like 20 spaces when defining a vector. That'd be ugly. Yeah, and then I put spaces after commas. I mentioned that. Yeah, and so it's not even like a functional thing at this point. We're just talking readability. And I think everything else is readability. Yeah, and so next I go over indentation and line breaks. And so this is when you start writing multi-line things. And so when you write functions that go over multiple lines or for loops that sort of span multiple lines, how to indent your code blocks. And so basically, whenever you're within a function or within another environment, An environment just meaning something is encapsulating the code that you're writing. You want to tab in or put, I guess, 2 spaces. I use 2 spaces as a tab. There's a whole tabs versus spaces thing. I think the standard tab is 4 spaces. In Helsinki, when I was a postdoc, everyone thought the tab was 3 spaces, and that was like the default. It's annoying. It's dumb. That's a thing, but I'm not going to go into that thing. So basically, if you had, I'll actually write this in the other screen, or I can just show you. So here, when I say get mean, I specify the function and I create that environment, right? I open the curly brackets, and the code that follows is still sort of encased within the function definition. In that case, I give it a tab or 2 spaces. So there you can see it's a tab, but it's the same thing as 2 spaces in this editor. That's why tabs and spaces is screwed, right? Because like tabs can be interpreted as any number of spaces depending on the settings of your text editor. Yeah, the same thing with an if statement, like I said. So, or a for loop. And the more levels you nest within, you just keep on spacing it, right? And so this is an if statement where I say if Brody is a cat or a cat, and then I indent and say, what should I do if that condition is true? And then I say print Brody is a cat. But what if I wanted another if statement within that? I would start it on that same indented line. So if, I don't even know, if a equals 0, even though we haven't defined a, let's not even do that. If 1 equals to 1, it's always going to do this condition. And then what I'll do is any code that's written in here has 2 tabs worth of indentation because it's nested within this code block here. And when yeah, and the way it closes the code as well is always in line. So if you start an if statement on a certain line or on a certain way with a certain indent, the end of that statement will come at the same indent, if that makes sense. And I think RStudio does this automatically for you, but I'm not going to buy into that, and I don't think you should either. I think you should just learn to write your own well-styled code without relying on a company that could be out of business in 2 years, or just change how they do things. I think that's the point of this course, right? We're not supposed to rely on other people. This is the idea of reproducible research. Limit your dependencies. Learn how to write good code. Yeah, I actually go into the whole tabs versus spaces here. I don't know why that's like a thing in my mind, but I think a lot of the R people will actually say that you should indent similar to this. And so here I start a list or a data frame or some object, and there's some belief that you should have as many spaces as it takes to get you to the vertical separator, I guess, between that argument, right? So if you're like 20 characters in by the time you specify the list, all elements of that list should be like there, all that white space, so you're going to go in 20 characters on it. I think this is a little silly. I think it reads ugly. I think it reads awful. And I think it's a recipe for having one of these list elements, in this case, span multiple lines. So let's say, like, instead of just saying peach, I'm actually calculating something. And so I have like a function call that takes a certain thing, or like first subsets data and then takes a certain thing, or manipulates data somehow. That could actually span more than one line. And then it just starts looking really bad. So you can write in this notation if you like, and I'll copy it over to the RStudio workspace so you can see it. Potentially bigger, so I apologize for the small text in this if you can't see it. But yeah, I just think it's ugly. I'm more of a fan of just sticking with this classic one tab in. And so treating the list as in its own environment and doing that. I'm also completely okay if you want to do something like that. but even that is like a little bit ugly to me. It's not really that bad. I'm fine with that actually. So yeah, it's personal style with some overarching general style rules. The last bit of style that I go over is just don't use the equal sign. Just stop it. Like that works. So if I want to specify a as a numeric value of 1, that'll work. And there are signs when you want to use equal sign, mainly when you define things that are named within data frames or lists or vectors. But when you're actually assigning some quantity to an object, you want to use the assignment operator, which is that. And so you wouldn't ever say like peach. So you wouldn't have double weird assignment operators here. This second one would be equal sign. I'm not even sure if that works. It actually does work. Oh, but it didn't name it. Is it because I didn't, oops. Is it because I didn't give it a character string, or did I not assign it? Oh yeah, okay, so it actually fundamentally matters. So here I tried to assign it using the assignment operator. Here I use the equal sign. Here it didn't take the name, I'm sorry. Here it didn't take the name, and here it did take the name. I actually didn't realize that functionality was there, but use the assignment operator to it. All right, so now we're going to switch gears and talk about line profiling. And so line profiling is a way basically to get at where in your code is the bottleneck in terms of either memory or time. And those are often the same places, but sometimes not. And so I waffled on how to introduce line profiling, because there's a lot of great packages out there that do line profiling in a much better way than BaseR does. Yeah, with some added functionality. And so there's the package lineprof, as I outlined here, as well as for code benchmarking, there's micro benchmark, which I've had a lot of good luck with. And I think there's also something called Tick, or not TikTok, that's a different thing. Is it called TikTok? I hope not. That would just be weird. I think it's just called Tick, T-I-C. It's been a while since I used it, actually. There's also really just, but these add dependencies, and I'd like to keep this course as dependency light as possible, and to really explore the functionality that is already within BaseR. Which I feel like a lot of people when they're first learning the language don't realize how much functionality is, because there's already so many packages. There's a huge ecosystem of color schemes and just packages, some of which are a little bit redundant and some of which are awesome. So it's a mixed bag. So the first thing I'll talk about when we go over memory profiling is the use of the system time function. And so the system time function, you bound it. And so system time is the outer bounds, and then whatever you want to do and measure the system time of goes within that. To be clearer about this, I give an example. And so here, inside the system time function, I'm taking 10 random draws from a uniform distribution bounded between 0 and 1. And so we can copy that over. Okay. And so here's the system time function. We have our open parentheses, we have our closed parentheses. It's going to tell me how much time did this process take. And we really, I guess, care most about elapsed time. System time is like how much time the actual computer took. Elapsed time considers memory transfer, is that right? Object transfer among, I don't actually know. I should know that. But regardless, elapsed time in my experience is like, I guess, closer to like true wall time in terms of how much time it's going to take for a process to do something. And so we see that to pull 10 random uniform variant, or to sample 10 values from a uniform distribution takes 0 time. And that's not really true. It just takes so little time that it doesn't profile it right. And then here, when we bump that up to, is that 1 million, 10 million? 3 zeros, no, wink in the eye, that's 1 million, counting those zeros. It takes 0.03 seconds, and so still very little time. So system time only really matters when you, basically what you're going to do is make a function call within that. So it's going to be I'm not going to write an actual function, but I'll write a function call that does a bunch of stuff. And so if you, ideally you'd write your code in a very modular way. So this is a function that like get species occurrences, get something else, and then you have a main function or something that where your functions interweave. So you call a function that you wrote within a function, and so that your analysis actually sort of completes not by this big long script of things, but just by saying, by these modular functions, and then finally there's some call that does a lot of work, depending on what you're doing. If you're just sort of interested in like a linear model between some variables in a data frame that you read in, that was not going to require you to write a lot of modular functionality. And I'm thinking more of like sort of long-running simulations or like complex like matrix operations and things like that. That would take some time. But this is potentially a little bit off, so I'm sorry if I'm just sort of missing on the on reading my audience. All right, oh nice, I specify what the different times are. So we have user time, system time, and elapsed time. User time, time charge the CPUs for the expression. Okay, so user time is computer time. Elapsed time, time for you, includes data handling steps. 0. Oh no, 0 is elapsed time. No, 0 is system time. I should reorder these. The difference between elapsed time and user time. All right, I don't know. I should know that. Doesn't matter. Like, still, the most important is the elapsed time, because I only care about me. It's time for me. It includes. Oh, I guess it is the memory handling or data handling steps that maybe is included in that. It's the time it takes for things to be transferred within the computer. I don't know. We're not going to worry about that. Yeah, and so a lot of times you'll have an entire script that you don't just want to wrap the entire thing in a system time call, because that's really clunky, right? So let's say you're like first subsetting data, and then you're running this convoluted function on it, and then you're like doing a bunch of simulations. You may want to like look at the line profiling all the way down. So line profiling is basically, so think of your R script as this continuum, let's go this way, this continuum, where each line is running a separate thing, even if you have like sort of nested things like an if statement that spans multiple lines. And what you want to do is actually get at how much computer memory and how much time you're using at each part of the code, in each sort of process as you continue down. And one thing you can use for that is in base, and it's rprof, so R profiling, and that it's capital R and then lowercase prof. And so you can it's basically like an on-off switch. So you can start it with this, which I'll copy over to the RStudio workspace so if you can read it better. That says rprof, and I've provided 2 different commands saying that I want both line profiling and memory profiling. There's like arguments to the function. Memory profiling equals true, line profiling equals true. Enter. Doesn't do anything, but now it's actually looking at what I'm running, and how you turn off the switch is using rprof null. And so let's run some code inside it. So this is a thing that basically creates between 1 and 1,000 dimensional Hilbert spaces multiplied by a random uniform variable. I don't know why I chose this. I think I chose it because it takes some time, to be honest. Okay, so now it's over. See, it took a little bit to run. Matrix inversions and things like that. So this takes the outer product of this thing. And I would turn it off. And what this does is create a file. And we can look at that file by looking over to the terminal. And now we're in the same working directory. So we can go to the console, say git working directory, which is git wd. It says that I'm in home/tad. That is the sort of Unix, I guess, desktop. I don't know what the equivalent is for Windows. And we can do the same here in the terminal, and it says same place. And then we now have a file called rprof.out. I think we have it. Yeah, there it is. Okay, sorry. So we have a line profiling file that is a log file that basically shows all this information about what it's doing, what function it's calling. So it's calling outer, just taking the outer product of something. We have the Hilbert function, which is just the overall function that's doing that outer product call. And now we can, but that's clunky, right? I don't want to open a separate file, and I'm like, I don't know what all this is doing. This is likely system time information. But R has some sort of, as a base thing, a base function to tell you about what's in that file. And it's summary rprof. It'll default to the file name that it defaults to, which is that rprof.out. And so we can just enter it without entering the function without any arguments. And we can see the time it took for each process. So let's just look at, instead of by self, we'll look at by total time. And we see that the Hilbert function and the outer functions were taking up the majority of the time with, yeah, they're taking up right around the same, I guess, ish. And then this also tells us the memory that's being taken up. And so of the entire process, not the entire process, sorry, which functions or parts of the script are taking up the most time computationally, so that's total time and self-time, or the most amount of memory, and that's total PCT and self-PCT. And we can look up information on, and then it also gives information on total sampling time. So that code took 8 seconds to run. And we can also look up summary rprof, and we can look at file name, and it gives us information on chunk size, etc. I'm trying to think if there's anything important or anything else important. By using memory in different commands, you can get at different things. And so if we actually wanted like a sort of time series of memory usage, we could use memory equals T series and show the memory usage in terms of time series. Because there's some things where the usage of the memory creates a large spike, or there's some times where it just increases slowly, or it just bumps up and then stays relatively the same. And you want to avoid, or you want to at least know if it's like the spiky type of code, because if it is, there's a risk of like your overall memory usage being around here, but if it spikes up at any given time, you could actually go out of memory in your machine. And in that case, RStudio shows you that stupid little bomb emoji and tells you that RStudio session's aborted or whatever. Or the terminal just says seg fault, or it just doesn't, and the computer just shuts down. All right, and so related to system time, and so now we're getting away from the idea of looking at how long something will take in time, as a process, and more caring about how much memory a process is going to take. And this is especially important to like sort of know the memory that you have in your computer, and to know the limit of what you can call within R. Yeah, otherwise you're going out of memory. It's never a good thing. So to that end, you can use built-in R functionality like object size. So object.size function will tell you in bytes how large something is. And so let's say we have this, this vector of length 10 that we're going to call A, and it's random draws from a uniform distribution. And then we can use the object.size function, give it the argument A, and it says that object is 176 bytes. And there's a bunch of cool stuff about sort of how this is stored, and like it's very sort of like step function-y, and some computer science lover is going to talk your ear off about it at some social gathering. And you'll love it. Or maybe you'll hate it. I don't know. It's pretty interesting, but we'll not go over it now. And then we can make a larger object. And so this is taking, that's 100,000 draws from that, from a uniform distribution. And then we can look at object size, object.size A2, and we see it's a little bit more in terms of bytes. To the same end, if we have something, so let's say we write a for loop and it's doing a process iteratively, right? So we learned that for loops, they go from sort of 1 till the process is done. So in this case, let's go, we're creating a list and we're starting from, looking at values from 1 to 10, creating random draws from a uniform distribution that are 10,000 values long, and storing it as object element I within this list A. So at the end of this run, we will have a list A of length 10, where each element in the list corresponds to a vector of length 10,000. And let's say we want to see the object size at each step of this function. We can toss this print command to object size of the list A as it builds, as it gets bigger and bigger throughout the loop, which is kind of useful. And so there we can run that code now, and we can see, so we set up the list element A, we start the for loop, we take the random draws from the uniform distribution and store it within A, and then we print to the screen the size of object A. And it starts out right around 80,000 and ends right around 800,000 bytes. Yeah. There's probably a way to get it to report in non-bytes, but in like megabytes, kilobytes. But you can just do sort of the math in your head. It's 80 kilobytes. Is that right? No, 800 kilobytes. See, I can't even do math in my head. I'm an idiot. All right, so for the last little bit, we're going to talk about error handling, which I feel like we may have touched on before, but I think we just, no, I think we touched on code documenting. We touched on code documentation. I don't think we actually touched on error handling. But error handling is important, and so it's one way to write really robust code. And what I mean by robust code is if I create a function that I use for an analysis, I call it get mean. And I like this function, it works really well. And then I release my code and somebody uses my code and they hand it a character vector. Why they want to take the mean of a character vector, they do it on accident. I want my code to be able to recognize that that's not how it's supposed to be used and to report something on that. So to error out, but to error out gracefully. So to say like, please supply a numeric vector. Don't supply a data frame, provide a vector. I can't work on lists, something like that. So like to basically just say limitations. And there's two ways to say the limitations when you're writing a function. The first is to say like a warning, like say like, oh, you might want to not do that. And then it still goes, like, so it still runs the rest of the code and just provides that warning. Or you can actually write to where it stops the functionality and it errors out. So it provides an error that says like, no, you cannot do what you want to do with this function. And I didn't even, it took me until late stage grad school to start really incorporating error handling into my functions. And even then, I still don't do it near enough now. And when I learned, I was an intern at HP, working on the analytics team for Vertica, which is their distributed architecture for running R in, it's called, they work on a project called distributed R, which is a way to run R parallel and do distributed data as well as distributed models. It was super cool, but yeah, I did not realize how much error handling had to go into functions. Everything, yeah, I wrote like some basic functionality, and the first draft was like 10 lines or something like that, and by the time I was done, it was like 40 lines of code that just was all error handling. That was an aside. So now let's see what error handling looks like in practice. So we created a function called isRead. So here I'm using the syntax that sort of tells the user that it's going to output either Boolean or it's going to make some sort of decision. And it uses the verb is. So you kind of know it's a function. So isRead, question mark, but I don't provide a question mark because yeah, that's bad practice as well. And so this function, as I have written it, can only tell if the object that you supplied to it, obj, is either a fire truck, a stop sign, or a clown nose as an input. So it only considers those objects as read objects. And then if one of those objects, or so if you provide it with an object that is not one of those three things, it just outputs or prints maybe, because it doesn't know, right? And so let's load it into R, and now let's try it out. And so we can say isRead, and let's say fire truck, and it says yes, but it outputs a nice informative warning message. And so you can see right here, I warn the user, this is a really arbitrary example, I warn the user that this function has really high error rates, right? And so if we say, what's something that's red that isn't one of these three things? What do we got? Like big red gum, something that's uniformly red. Stop sign, I guess clown noses aren't like uniformly red. Blood. Why did I think of that? That's not all. What am I doing? It says maybe blood's red. Sometimes it isn't. Sometimes it is. Depends if it has oxygen in. Regardless, yeah, and it still provides that warning message because that warning message is outside of the two if statements. All right, and so now I sort of go into the differences between warnings, so this function prints that warning every time, regardless if you hand it anything. And so this you can hand it something numeric, and it'll still put the warning and say maybe. Maybe 1 is red. It's a silly example. And so now we want to like control that, right? We want to not be able to hand this function numeric values and have it return anything, because that's sort of silly. And so we use error messages, which stop the function from proceeding. So I'll run this line by line. And so now we recreate the isRead function. And so we see isRead, the function call. It takes one argument called obj or object. It submits a warning saying like, hey, don't trust these results. This has really high error rates. Then I have a conditional statement and say, if obj, the object that you provide the function, is numeric, then do the following. And the part that it does, or the doing of the following, is the function stop. Stop is the same thing as saying like create an error, break from this function and error out with some informative error message. And we provide this informative error message as a character string within the stop function. And so this says, if I hand it something numeric, say like, just stop what you're doing and say, obj or object is numeric, not a string. Only accept string. And then we end that, and then the rest of the functionality or the rest of the code is the same as it was above. And so now when we say is red fire truck, it says yeah, but it warns us that that there's really high error messages. And I can say is red the number 1, and it says error. Doesn't return anything. It says the error message, and then also in addition gives us the warning message. All right. Nice. Okay, so the last little bit that I'll go over is about unit testing. And for that, we are going to need a dependency. And that dependency, I think, has a lot of subdependencies, actually, if I'm not mistaken. The dependency that we're going to use is called test that. And it's really great for doing unit testing. And so unit testing can be really good for sense checks when you're working with differently structured data. So if you know what the output's going to be in terms of size or in terms of dimensionality or some other aspect of like data or analysis or object structure, you can use this package to make sure that that's the case. And that's providing unit tests. And so let's say I don't trust that the mean function is doing what it's supposed to be doing. I can test that using test that. So we call it in test that. Let's see the session info. What else is it loading into our? Yeah, it's just loading in a bunch of the, or no, I already loaded dplyr to 2, didn't I? Oh no, I didn't, it's not attached. So this is just test that. And these are all the packages that are sort of loaded in via namespace, but not attached. So like things that I think that qualifies as suggests, maybe. It shouldn't be depends. It should be just suggests. But still, it's a little bit of a convoluted web we weave. All right. I'm reading my notes really quick, so I make sure I go over this sort of in the best way. And this is actually a fun side note, is that like I use unit tests actually to grade your homework. And so when you write code and your R code, I write unit tests that basically say like, oh, is this of the right dimensions? Is this the right value? Is this equals to? Is this less than? Is this blah, blah, blah? So that at least for some of the assignments, Travis grades it automatically. Travis is the continuous integration framework, which I think we've briefly talked about, which should become hopefully clearer to you in the future. And it's very fun. And it's confusing. It's quite confusing sometimes. So don't feel bad when you mess things up, because I air out all the time with Travis. Yeah, I provide a good article, and this is an article that we will read and discuss in class, which goes over the test that package in detail, which is really nice. And so typically when you write unit tests, you want them to not be within the same file as your code. You'd want them to be in a separate file or folder, and sort of the tradition, how the style that I've normally seen unit tests, especially ones that use test that, which is like the de facto unit testing framework, is to create a separate folder called tests, and then within that having a meta script. No, what is it called? Test that? No, you have tests folder in your analysis directory, and then a file called testthat.r. Doesn't need to be called that, it can be called whatever. That basically just gets source and runs the individual tests that are within that test folder. If that makes sense. I'm sure I have like an example just around here that I can show. Let's hop over. What did I just do? I'm going to my GitHub and looking at at the Metacon package that I developed. Yeah, it's a folder called tests, and then within that, another folder called test that has all of the individual tests, which are R scripts that run a specific test. And then you have a top level script that's still within that tests folder, and that contains the R script that actually runs all the tests. And so the test that package has, is it test all? No, what is it? Testdir is a way to run all the tests in a given directory. Tests are also incredibly useful for writing R packages and getting like your code coverage, not really getting your code coverage down, but at least getting like your test coverage down, meaning like you want to test as much as you can. And when you test an R package, it's just the test check function, I believe. Yeah, run all directs in a directory or package. Oh, so that'll actually also, even if it's not an R package, it'll still run the tests for the code. So how you want to typically structure your tests when they're separated out into separate files, you want to test certain functionality of your code. And so I guess it's easiest and cleanest to test the output of a given function. So if I wanted to test isRead, that's the example that I give. If I wanted to test how isRead is doing, I first provide a context. You don't strictly need this. The context is just a way of grouping different tests in some sort of hierarchical subset, providing you with many contexts and multiple tests within each context. So here I'm trying to test that isRead is doing stuff. So I'm focusing on the function isRead, and I'm using different functionality. So I'm calling test that functions. Hopefully you can see this. I forgot how to zoom in. I can figure it out really quick. Go to preferences. No, use system font. Let's just ramp it up to 18. Ooh, all right. Not forget to change that after. Okay, so now I know you can see that. I really hope that you can see that better. So here's the structure. You test that and you provide the function context, and you give it a new character string that provides the context. And then when you have the actual test that is an environment. And so you say test that, you start that function, and then you provide a bounded group of testing. They're bounded, or a group of tests bounded by the curly brackets. And so here I write 3 tests that are related to test that. And the first test is using, so all tests start with the verb expect. And so they will either output nothing, which means the test is passed, or they'll output an error and say like, no, this test is not passed. This is a flag. Everything's not cool. And here I test 3 things about the isRead function. There's Brody Cat making her appearance, saying hi. All right, I'm setting her another chair that I have, so she can keep me company. She's just gonna jump right back up on the desk. So I'm testing 3 things. The first is that I'm expecting that the output of blank is equal to blank. That's the structure of the function. In this case, I'm expecting that the output of isRead, my function, but calling orange is maybe. And we can run that. And it gives us the same warning message that isRead always does, but it doesn't give us anything else because that is the correct output. I also can expect different things. So not just that I expect that the raw output is maybe question mark. I can also expect that what sort of type or length or dimensionality that I expect. So in the second test, I have expect type of this call to isRed, which I give it clown nose, and I expect it to be character. I expect it to give me a character string, and it does. It should give me a character string either way, whether it's clown nose or whether it's any other character string that I provide. However, if I give it a numeric value, it will error out. Remember that. And then lastly, or this is just one more example, there's a bunch of different expectation statements that all start with expect underscore. And here it's expect equal, and I expect that the length of the output of this function call is 1. And we can run that, and it is. It provides the actual output. It didn't appear. I don't know why it didn't. But if we run that entire thing, we should see. Yeah, it outputs stuff. It prints to the screen, but it doesn't really matter because it doesn't actually error out. And we can look at it when it errors out. Do I do that later? Oh yeah, I do that right here. So let's break the test condition. Let's make it so that it's wrong. So here, I'm expecting the type of output of isRed to actually be numeric rather than character, even though I know it's going to be character. What happens if I expect it to be numeric? And there it provides a clear error. And that error is the flag that says, whoop, we didn't meet this unit test. isRed, a clown nose has type character, not numeric. And that's different from the error that I wrote about if you handed a numeric value, just to be certain on that. Birdie's trying to sit on the keyboard, which is never a good sign. The more you try to stop her from sitting on the keyboard, the more she wants to sit on the keyboard. And there's other useful functions within test that. And I list them in the lecture notes right here. I sort of went over the ones that I use the most, but that's just personal decision. Because there's also expect null, so you can expect that the object's going to be null or invisible. I guess null. You can expect true. I think there might be expect false. I don't know. And then different sort of conditional. So expect that. Yeah, that's Brody typing. You can expect that something is more than, something is less than, identical to, equal. You can expect that it will produce an error. And so if I said expect error isRed 1, so I give it a numeric value, that would actually be a good thing. It would pass that unit test because when I handed it that value, some idea of what I expect it to be, so the expectation matches what is actually there, then it passed the unit test, which is good. I talk a little bit about code coverage, in the notes, but I don't really need to go into it here. The idea behind code coverage is you want all of your the functions and the bits and bobs within your code to be covered by unit tests. So the idea of code coverage is that how much of your functionality within your R package or within your function base is covered by unit tests. So higher code coverage, the better. Because ideally, or like putatively, that your well-tested code is more robust against errors and handles errors more gracefully. All right, and so that was a lot of information, and we'll go over a bit more within, like in the other lecture. But I think this is a good place to stop, and we've covered a lot of material related to best practices in how to write good code, meaning clear code, as well as writing good code in terms of not maxing out your machine's memory or taking too long with line profiling, and then writing good code in terms of well-tested and robust code that provides informative errors when it does error out and informative warnings when it doesn't error out. So yeah, it's fantastic. I'll see you guys in the next lecture. Stop sharing the screen. And take care.